Now let's talk about non-parametric method for density estimation. And histogram is a good example to explain what non-parametric method is. And it is a simple non-parametric method, and it divides the sample space into bins and counts the number of samples in each bin. So let's say in this example, we have one-dimensional sample space, and we divided this sample space into bins. So this is one bin, so we have lots of bins here, and then we count the number of samples in each bins. So in this bin, how many samples do we have? So we count the samples for all the bins, and then we normalize all these numbers to be a probability mass, because when we sum all of them, then it should be 1. So we normalize. And then, as you know, the non-parametric method doesn't have parameters. Usually the parameters are updated during the training process. But in the non-parametric method, we don't have that kind of parameters. But we have hyperparameters. So these parameters are not updated during training process. So we have a 2. So first one is bin width. We can change the size of the bin. If you want, you can have a bigger bins. And when the bin size is big, then we have more samples. Okay, but the resolution is just low. And then we can choose a starting point. We can start from here or from here or from here or from here. So depending on this starting point, the position of each bin would be different. Okay, then the number of samples in each bin would be different too. So these hyperparameters matter, but not that significantly. We have a couple of drawbacks. The first one, this probability mass depends on the starting point and the bin size too, but that is not that critical problems. And another problem is that it is discontinuous. Okay, discontinuous means look at these two bins. Okay, so when we change slightly in this sample space, the probability drops a lot. This could be a problem. And the next one, which is more important, is that there is the curse of dimensionality. So in this example, we have one-dimensional sample space. But if we increase the dimension of this sample space by adding more features, then we need more samples. So when the sample space is low dimensional, then a few samples would be enough to estimate the density. But when we increase the dimensionality, then we need a lot more samples to estimate the density, because otherwise most of the bins will have just 0 samples. Okay, then it's really hard to estimate. We're going to talk about two major approaches to estimate the density with non-parametric approach. Then before talking about these approaches, we need a couple of equations. So let's go through these equations. First, given this density, so P of x is given, okay? Then the probability that x is in a region, a specific region R of the sample space can be calculated in this way. So let's assume that we have P of x here, and then we have a region here. Okay, so the probability that x is in this region is actually this area. Okay, and then this area can be calculated by this integral. Okay, and then with n samples, the probability that k of n samples are in the region R is this. So n combination k times p to the power of k times 1 minus p to the power of n minus k. Because out of n samples, we have k samples in the region. And one sample is in the region with this probability. Okay, so first we have to select k samples out of n. So we have n combination k. And then since k samples are in the region, so we have p to the power of k. And then n minus k samples are out of that region. So the probability that x is not in the region is 1 minus p. So we have 1 minus p to the power of n minus k. And this is the binomial probability mass function. So the expectation of k over n is p. And the variance of k over n is this. Then as you can see here, as n goes to infinite, then the variance will converge to 0. Okay. Then when the variance is 0, then p is k over n. So approximately we can say p is k over n. And then if r is really small and the volume is v is the volume of the region, then we have this equation. So the volume is actually a general term. Okay, when the sample space is one-dimensional, the length is volume. Okay, and then when the sample space is two-dimensional, then area is the volume. Okay, and then when the sample space is three-dimensional, then something like this is the volume. Okay, so volume is a general term. And as you know, the p is integral p of x in that region. Okay, and then if you look at this example, probably that x is in this volume is actually this area, right? And then this area can be approximated by this rectangle, even though there is a gap, right? So even though there is a gap, but still we can approximate this area with this rectangle. And if this area is small, okay, then this gap is smaller. Okay, so as the area is really small, then the difference is really small. So we can approximately we can say that, you know, when the r is small, then we can say there is constant probability. With that constant probability, we can approximate the p. Okay, now we have pretty much everything. So from the previous slide, we have this one. And from here, we got this one. And if you look at this equation, then as n increases and or v shrinks down, then p of x becomes more accurate. Usually when it increase n, okay, then probably k would increase. Because we have more samples, then probably we might have more samples in the region too. And when the v shrinks down with lots of samples, then also p of x becomes more accurate. But in practice, n is fixed. So when we start working on machine learning, usually the number of samples is fixed. And there is another interesting point here. V should be large enough to include enough examples. Because if V is really small, then most of bins will have just 0 samples, then it's not easy to estimate. And also it should be small enough to make p of x constant in the region. So it's tricky things. We have to control this V really carefully. Okay, so now we're going to talk about two major approaches to estimate the density with the non-parametric method. Okay, before talking about it, I'm going to give you one simple example here. So we have 1D sample space with the variable length. So it looks like this. And then p sub I, the probability that one sample is in this bin is k sub I over n. And p of x is p sub I divided by L sub I. So this one is straightforward, right? So when we have lots of samples here, let's say we have 6 samples and in total we have 10 samples, then this one will be 60%. Okay, that's what this equation says. And then this one is 60%, 0.6, but the length is, let's say, 6. Okay, then each one is 0.1. Okay, 0.1 times 6 is 0.6. So P of x is P sub I divided by L sub I. L sub I is the length of the ith bin. So in general, instead of L sub I, we can use V sub I for the volume. Okay, and then P of x is K sub I divided by N times V sub I. So we just combine this one and this one. Now, there are two approaches for density estimation with this equation. And as I said, N is usually fixed. Then we can control K sub I or V sub I. Okay, first one, fix V, and then we determine the K from data. We can check how many samples are in the bin. So that is actually kernel density estimation approach. And second one, we fix K. So we fix the number of samples in the bin, and then we increase V to include K samples. So K nearest neighbors would be the most popular example for this approach. And if you have some knowledge about this machine learning, then probably you might know this KNN as a classification algorithm. But in this chapter, we are talking about this KNN as unsupervised learning to estimate the density. Okay. So first one is kernel density estimation. The simplest approach is to use Poisson window. From the previous slide, we have this one. And as I said, in this kernel density estimation, we fix volume. Then we have to check how many samples are in the volume. So Poisson window has a window like this. This is a window. And then we just count how many samples are in the window. So Ki can be calculated in this way. This equation looks a little complicated, but it's really simple. Just counting the samples in the window. So look at this one. We have x here, and we want to estimate the probability of x, P of x here. Then let's say we have to provide bandwidth as a hyperparameter. And if this is h, then we just check x minus xn divided by h should be less than 1 over 2. Then it is 1. So look at this one. So x minus x3 is smaller than h over 2, right? This one is h, and this one is h over 2. So it is 1. And x4 is out of this window, so it is 0. So we just simply count the samples in this window. So since k is defined in this way, so probability based on KDE is simply like this. Okay. To help you to understand this KDE approach, so let's take one example here. So we're going to calculate the P of x at 3, 9, 15 with the bandwidth of 4 and the 10 samples. Then let's calculate P of x is 3. Then it is 10 is the number of samples and the 4 is volume. And then we just count, okay? This is the count of the samples within the window. And we just check all the samples from this one. So this is the window because it is 4. So this one is within the window. So it is 1. And this one, all these samples are not within the window. So these are zeros. And how about this? P of x is 9. Then all the samples are not within the window. So these are all zeros. And how about 15? So when we draw this window size, then we have 5 samples in the window. So we have 5. And the other ones are zeros. So this is how we calculate the probability with the KDE. This is quite simple and intuitive. Okay, that is based on the Poisson window. And the Poisson window is just rectangle. And the density is discontinuous. This is another kind of problem. So instead of having this strict window size, we can have a smooth corner. Because when we have a samples here, we have a 3 samples here, or we have a 3 samples like this, with Poisson window, there's no difference. Even though the samples is really close, then we expect that the probability should be a little higher than the other. But the Poisson window cannot tell the difference. But smooth corner can tell the difference when the samples are close to this or the samples are spread out. Okay, so instead of just a strict window, then we're going to use a smooth corner for this K. So this corner function can be defined by this, which looks like Gaussian, right? So it is actually Gaussian corner. With each sample, we have Gaussian corner functions like this. So since we have 8 samples, we have 8 corners, and then we just sum them up. So finally, we have this density. It looks like this smooth distribution. And it depends on the bandwidth, h. So h is small, then each corner is sharp, like this. Then when we sum them up, still we have sharp bumps here. And when we increase the bandwidth, then we can have a smooth distribution. And when the h is too large, like 5 or 10, then we have just one smooth curve. This is not what we want. So we have to control this bandwidth really carefully. And the next one is k nearest neighbors. Okay. In this, we fix k. Okay. And then we control the volume to include k samples. And the k is hyperparameter here. So let's assume that the k is 3. Then to estimate the probability at these locations, then we have to increase the volume to increase 3 samples. So this is our volume. This is radius. Then the volume is pi r square. This is volume. Okay. And when the k is 5, then this one is not enough. We have to increase r like this. So now we have 5 samples. If we are interested in this location with k of 3, then this is our volume. And if we have the point here, then the volume size would be like this to include 3 samples. Okay, so depending on the location, then the radius would be different to include 3 samples. So based on this, we can estimate the density. So let's say this is a true density contour. From this true density contour, we generate lots of samples. And then if we estimate the density based on the k and n, then it looks like this. So it looks similar to this one, but they are not smooth contour. If we increase the number of samples, then it will get smoother and smoother. Okay, so far we talked about parametric method and non-parametric method, and the last one is semi-parametric method, which is kind of the hybrid, which is in between these two extreme cases. So it's a very general class of functional forms, and to build more flexible models, we can increase the number of parameters. And usually mixture distributions are considered, like a mixture of Gaussian. So we're gonna learn this thing in detail in clustering chapter. In this slide, so let me tell you the brief idea of this mixture of Gaussian. in the parametric method, we can assume that the density is Gaussian, and then we have to estimate the mean and the variance. Okay, so there is one distribution with the parameters, and in the KDE, kernel density estimations, we have lots of kernels. So when we have like 10 samples, then we have 10 kernels. In this case, mix of Gaussians, we have many Gaussian distributions. So in the parametric method, we have just one. In the non-parametric method, we have n Gaussian kernels. And now we have m Gaussian distributions. Okay, and each one corresponds to one cluster. So we have one Gaussian here, and another Gaussian here, and another Gaussian here. And then we have to find the best kind of weight for the distributions, because without this, this is not a probability. So to make it probability, then we need this one, mixing coefficient. So again, in the parametric method, we had just one Gaussian distribution. In the non-parametric method, we had n Gaussian kernels. In the mixture of Gaussian, we have m Gaussian distributions, each of which corresponds to one cluster. So that is kind of between these two extreme cases. Okay, this is it. Thank you.